Okay, let's look at 14, and we'll take a peek at 13, which is the null and alternate hypotheses are that mu1 is equal to mu2, and keep in mind yours is different. Mine's a two-tail. 14 is going to be a one-tail test, and so you have to keep that in mind as you're finding your t statistic, right? Okay. So here we go. First it says, and we got to do, if you look up above again, it says determine the numbers of degrees of freedom. OMG, you know, go back to page 361, and right there, about 2/3 of the way down, it says degrees of freedom for unequal variance tests. So now what we're doing, right, remember we were assuming before that we had basically equal variances, and now we don't have equal variances. And so how do we determine our degrees of freedom in order to calculate our test statistic? Oh, well, we're going to use this formula, okay? And you know, if you wanted to put all this into one line up here, have fun. Okay, this would be really difficult, and so obviously I've broken it up, and you might want to break it up even more than this, and that's fine. And you might want to write it out, you know, and make sure that as you write it out, you can have the calculator have this do the, you know, the calculations. But make sure you show your work, okay, so I can see what you're doing. But remember, we got to do all of this. Okay, up here, this is divided by these, both of these formulas down here added together. So wowzer, here we go. So first let's get our information, right? A random sample of 15 items, so my n1 is 15. From the first population showed a mean of 50, so that's my mean of 50, right? And a standard deviation of 5. Okay, and the second one is a sample of 12, population mean of 46, and a standard deviation of 15. Okay, so quite a big difference in standard deviations. That's why we're assuming that they're unequal, right? So this is just the variance divided by, right, the sample standard deviation squared, or the variance of 1 divided by the n of 1, or the sample size of 1, plus the variance of 2 divided by the sample size of 2, and we're going to square all of that, right? And if you follow and you put the parentheses in just like they do, this will be fine. So I'm just going to do the top part. You'll see I've kind of labeled it that way. So this equal to, and I'm going to need 2 parentheses there according to that. So it's going to be equal to my S1 squared, okay, divided by my n1, okay, and parentheses, right, plus my parentheses, my s2 squared, s2 down here, squared, okay, divided by my n2, and parentheses, and all of that then is going to be squared. Let's hope I did it right. See if all my other numbers change. They didn't, so I must have done that correctly. So I got the top part done. Okay, and then I divided the bottom into bottom left and bottom right. And obviously I'll have to add those together, so it's really quite simple, or quite similar. Simple too, it's just a lot of numbers, but the bottom left, so then is equal to, again, you're going to need maybe some extra parentheses here, right, because I'm going to divide this by this, and yeah, that's going to need an extra set of parentheses. So add 1 set to what you have here, basically. So it's equal to 2 parentheses again, the variance of 1, or the standard deviation squared, divided by the n1, okay, and that whole value is squared, okay, and then it is divided by parentheses, n1 minus 1, or 15 minus 1 in parentheses. Hopefully I did that one right. So far so good. Okay. And then I would do the same thing for the bottom right. Okay. And I won't belabor you with that, but just go through the same process, except it's S2 and N2, right? And there. Okay. Then I got to add those two together. So this plus this. There we go. Okay. And so now my top is 416.84, and my bottom is 32.1586. So now I just have to divide those. This divided by my bottom, and I end up with degrees of freedom equal to 12.96. I have a feeling we're going to round up. I think we always round up if I'm not mistaken here. We'll take a look. Okay, my significance that I'm looking for is, oh, does it tell me what my significance is? Oh, at the point, it says use the 0.05 significance level at the top. Now again, I'm a two-tail, you're just a one-tail, so keep that in mind. So my degree of freedom, I said, was 13.05 in the two-tail. Okay, so it looks like 2.16 should be my statistic, right? I got 2.179. Where did I goof up there? Maybe, did I round up? Did I hit the right number? Let me go back and see that. So I got 13 and 0.05 on the two-tail. Ooh, you round down. Okay, you always round down, it looks like. So I got 2.179. Let's go see. I'm going to go check in the book and make sure that I'm right about that we do need to round down. Sure enough, right there on page 361 again, right below the formula, it says, if necessary, this fraction is rounded down to an integer value. An example will explain the details. So we always round that down. Okay, so I would look at my 12 as my degrees of freedom and my two-tailed test 0.05, so I'm at 2.179. Okay, so I'm going to reject again because it's a two-tailed test if it's less than minus 2.179 or greater than 2.179. So A, I've calculated my degrees of freedom, and B, I've stated my test rule, my rule. Okay, and then C is, what do I got for C? It says state the decision rule. C is compute the value of the test statistics. Now I just do my normal T one here, right? And again, we've done those before, so I'm not going to really bore you with that, but I get the mean of 1 minus the mean of 2, so 50 minus 46 is equal to 4. You know, over that, do the square root, okay? And so my calculated T statistic ends up being 0.8852, right? And so, see, I'm going to reject the null, okay, if it's greater than 2.179 or less than. It's not. Okay, it's not greater than. Okay, and it's not less than a minus 2.179. So I'm going to fail to reject the null. Okay, I will reject the alternate, but I will fail to reject the null hypothesis. Was I supposed to state the hypothesis? Okay, nope, it doesn't tell me to state the hypothesis. So I would just fail to reject the null hypothesis in that case.